Hello, my name is Rob Reynolds. Welcome to Calculus Section 5.1. Today we get an introduction of integration. So we've looked at derivatives for this first part of the year. The second part of the year is integration. So how to undo. And then derivatives, of course, deal with velocity being the first derivative, acceleration being the second derivative. Integration deals with area underneath the curve. So the first thing I need to talk to you about is the difference between distance and displacement. So the distance around a rectangle would be adding up all the sides, twice the length plus twice the width. So if you were to travel 6 here, then 2, and then 6 back this direction, and then 2 down, your total would be 16. But if you go and start here and then travel here and then travel here and then travel here and then travel back, your displacement is 0. So that's the same thing about area underneath the curve. The area underneath the curve here is length times width, 2 by 6. 2 times, well, excuse me, 2 times 60. So it's 120 miles if you put it in this form. So the area underneath the curve here, you might think, well, this is positive, this is negative area, so the actual displacement, which you should always think about when you're talking about this integration symbol, that's always like positive area plus negative, so it's net area, then the displacement is 0. Now, if I just would have asked what's the area of this, then you might want to ask, well, area is usually the absolute value. So if the area of this black is 10 units, then the area of this would be negative 10 units, but the area then would be 20 units altogether because you would take the absolute value of a negative and make it positive. So if they just ask for area or total or absolute area, then I would say 20. But whenever I integrate, I get displacement. So our first example says, let's divide this function into 8 partitions, or excuse me, 2 partitions from intervals 1, 0. So the square root function looks something like this. I could probably get a little bit more accurate because I could actually find some points off of this thing. But accuracy doesn't really matter. So in this example, I just need to go from 0 to 8, and it does say divide into 2 subintervals. So I'm going to go from 0 to 4, being 1 subinterval. And I need to read carefully. There's another key word up here, and it says midpoint. And so if I were to go from just 0 to 4 like this, that's not the midpoint. That would be a left-hand side. So I think to grab the midpoint, I'm going to go up just a little bit higher. So, but the midpoint between 4 and 8 would be the 6. So this is the rectangle that they want that's going to hit the function at the midpoint 6. And then the other interval is between 0 and 4, which of course the midpoint is 2. So that rectangle would look like this. So for part A, my first rectangle, the width is 4. So all I have to do is width times height. So width times height plus the next width times height. Well, the width is 4. Well, by the way, the width here is 4. The height is f of 4, the function evaluated at 4 units. No, the function evaluated at 2 units, excuse me, 2 units. And then 4 times the function evaluated at, see, this is 6 comma f of 6. So we'll say 6 comma f of 6. Of course, I could just factor out the 4 to make this easier. And then these are all my heights. So I'm going to evaluate the function. Actually, it's a v sub 2, and because the function was defined not as f, but as v of 6. And so now I need to do some evaluation. The function, well, this function is defined as the t squared function. So this point is 2 comma 2 squared, or 4, plus 6 squared, or 36. Probably should put the parentheses there. It's a little confusing. Let's put the parentheses there. And that's 160. So for part B, they changed the interval. Well, it's still between 0 and 8, but my subintervals are 4 subintervals, and I suppose I'm still doing the midpoint. So I'm not going to draw it here, but the midpoint between 0 and 2 would still be, well, midpoint here would be 1, but notice that the width has changed from a width of 4 in the first example to now only widths of 2. So just like I had the width of 4 before, now I'm going to have a width of 2, and I'll factor that out. So 2 times all of the v sub midpoints. And then the first midpoint is at 1, plus v sub the next midpoint is at 3, followed by 5 and 7. So 2 times 1 plus 9 plus 25. All I'm doing is squaring these things because that was the function, and then evaluating 168. Let's try one last one. Part C, 8 subintervals, assuming still just the midpoint, of equal lengths. That means that they're all lengths of 1s. So delta x is what I'm going to start using for the notation of the width. And it's going to be defined as b minus a over n, where b, here's your a, here's your b, so it's 8 minus 0 over, and then n would be the number of subintervals. They tell me that n is 8. So 8, so you can see delta x, which just means the width of each rectangle, in this case is just 1 for part C. And then it's going to be v sub the midpoint. Now the midpoint between this first little rectangle right here is going to be 1/2. Plus v sub, and then I just do the width here, just delta x, because I'm just going to add this distance is going to be the next midpoint. So that's 1.5 plus v sub 2.5 plus all the way to v sub 5.5, keep going, all the way to what, 7.5, v sub 7.5. So add all those up, and you can see that I'm getting a better and better estimate. So the more ends I have, the more partitions I have, the better estimate I will have. I think this is like 42.25 for the second to the last one, and then 56.25 for the very last one. And if you add that up, you get exactly 170, which is a pretty good estimate of what that area underneath the curve would be between 0 and 8. So if I push n to the limit, I would get the exact area underneath the curve. So here's a little bit better representation of some figures that are drawn. And you can see there's less and less error the greater n is. So if you keep pushing n from 8 to 16 to 32 to 64, you even get closer. So you thought maybe 170 was the exact answer, but it actually approaches something closer to 170.656. So here's the definition of the width that I gave to you that we're going to be using for delta x. It's the width of each rectangle. And then remember, a and b is just the interval that I'm interested in underneath the curve. This looks intimidating, but I'll explain that in a minute. This is what's important for now. And then this f of x star is what we were doing before when you evaluated the height. So here's your height, and of course we've already defined delta x as your width, and that's where you get all your little rectangles. Now we do have left rectangles and right rectangles, and I've only done an example of the midpoint rectangle. So let's look at left and right. These are called Riemann sums. So f of x star is the first height, this is your second height, and so on and so forth. And then your width should always be constant, and that's why we're just going to factor those out. But if you're doing a left Riemann sum, notice that these rectangles always hit the function on the left side. And just for this particular example, it's an underestimation, but the left is not always an under. It depends on the curve. So this is a right Riemann sum. You can see the rectangles hit the function on the right. Sometimes it's an underestimation, sometimes it's an overestimation, just depends on what the curve is. And then sometimes people think the midpoint's always the most accurate, but it's not. I like midpoint, but that's the example that we already did. But sometimes the midpoint can be the most accurate. So let's look at left, right, for example, number 2. This happens to be a sine function, and if you remember anything about trig, your sine function looks like this, but I'm only interested in between 0 and pi over 2. So I'm only interested in this little portion of the area underneath the curve here in green. And the first one says divide this up into 6 subintervals. Well, if I have 6 subintervals, that's pretty tiny. So let me bring this to life for you. Here's that axis right there. So I'm going to start with 0, and I'm going to end with pi over 2 and just kind of make this a little bit bigger. And I need 6 subintervals. So let's do our delta x is b minus a over n and find out what's the width of each rectangle, because I need 5 of those little tick marks in there. And I just didn't want to squeeze it in there, so I'm going to make a little bit larger number line here. So the end is pi over 2, the beginning is 0, divided by 6 is pi over 12. So I'm going to start counting by pi over 12s. 1 pi over 12, 2 pi over 12s, I can reduce that. 3 pi over 12, I can reduce that. 4 pi over 12s, yes, I'll reduce that. And 5 pi over 12s, I can't. And then 6 pi over 12 is back there, and I've got my 1, 2, 3, 4, 5, 6 regions. Perfect. And I've got delta x. So here comes delta x times f of x star. And I've got a lot of those x stars because the heights keep changing. Now, careful. Who do I want to do first? Let's do left. So the first x star for part A is going to be delta x pi over 12. And on the left, it starts with a height of 0. Maybe I could do f of 0. That's still 0. The height is 0 because that's the left that it starts with. And then I'm only going to grab the left. So 1, 2, 3, 4, 5, 6 intervals on the left. Those are the only ones I'm going to grab. So I started with 0 plus f of pi over 12 plus f of, well, this is pi over 6. This is pi over 4. This is pi over 3. And then I end with 5 pi over 12. And most of these are on the unit circle, and you can evaluate these, but this will turn out, remember, this is the sine of 0. Most students here would just punch it because I don't know what the sine of pi over 12 is. I do know that the sine of pi over 6, I hope you know that too, is 1/2. But at this stage of the game, I think I would just punch this into the calculator, multiply by pi over 12, and you'll get 0.863. If you can't, shoot me an email and we'll find out what the correct answer was. For part B, it's the right. So instead of using this 0, I'm going to start here. So that's my first f of x star. So I'm still doing delta x times f of x star, but my delta x is still the same width, pi over 12, but I don't start at 0 on the left, now I start on the right. So I'm going to do f of pi over 12 plus the pi over 6. I can just read them from right up here. Plus f of pi over 4 plus f of pi over 3 plus, I'm reading up here, f of 5 pi over 12. And then I'm going to grab the right one, ending with f of pi over 2. And again, I'll punch that. Remember, when you punch it, you want to type it in the sine of pi over 12 plus all of those, and multiply by pi over 12. And on this one, you should get something close to 1.125. So this looks like an underestimate. This looks like an overestimate. And the next example is the midpoint, which I suppose is somewhere in between. So there's the author's answer for your underestimate. There's your author's answer for the overestimate. And let's just finish this up with the midpoint. So for example 3, I've got the exact same thing as I did before between 0 and pi over 2. But this time I'm going after the midpoints. And so I have the same interval, I believe, 6 subintervals. So I believe my delta x is still staying pi over 12. But I'm not going to grab pi over 12. I'm grabbing the midpoint of pi over 12, which is pi divided by 24. So the delta x f of x star, the sum of that would be, and of course I can just pop out delta x because it's a constant, would be the pi over 12 times the sine. I'll just go ahead and go to the function and plug in the first pi over 24. Then I go to the next sine, and remember, this distance is also delta x. So all I have to do is just keep adding pi over 12, or really 2 pi over 24. So I'm just going to add a 2 to that 1 and end up with 3 pi over 24. And then I continue this. The question is, when do I stop? Just keep adding 2 more pi's. So 5 pi over 24, and then keep going. 5, 7 pi over 24, 9, 11 pi over 24. And then I don't think I can go any higher because then I would be beyond the pi over 2. So I'll stop at the 11 pi. So punch this in, again, using those signs, and see if you don't get somewhere close to 1.003. Again, the author might have done a little bit better job of explaining where all those came from, but there's his worked out solution. So for example number 4, kind of repeats example number 1 and 2. I'll kind of leave this for you to do, but remember, if they ask for the left, you're going to use the 0, the 1/2, the 1, and the 1.5. But if they ask for the right Riemann sum, then use the 0.5, the 1, the 1.5, and the 2. And again, I do have that worked out here for you. So there's your left, and then here comes your right. And if you have questions about that, you can shoot me an email. But I wanted to spend just a little bit of time with these sums of k's, which you do not have to have memorized, and I will provide for you a cheat sheet for the sums of these k's. This becomes really important. The sum of k squared, the sum of k cubed, or even the sum of k and the sum of a constant. So this is what I'll provide a cheat sheet for you. You don't have to memorize this, but you need to know how to use that. And I'll post that cheat sheet on Blackboard. The other thing that will be on my cheat sheet will be this x star business, which we know is part of the Riemann sum that I need. Well, if I'm doing a left x star, I start with the first term because it won't always be 0. Then I do k minus 1 times delta x. If I'm doing the right Riemann sum, x star's definition changes just a little bit. Well, it kind of makes sense. Instead of it being minus 1, it's just the k times delta x. I like that definition because this is the easiest one to work with. So if it doesn't specify left, right, or midpoint, I would always choose the right. And just between you and me, because you're listening to the video, the test will be a right Riemann sum. But your homework assignment, they'll ask you to do a midpoint, and in that case, you'll do a k minus 1/2 times delta x. So here are those definitions. Again, you don't have to have those memorized. I'll provide that cheat sheet, and I think it's posted on Blackboard, but if it's not, I'll make sure it's there. So here's what I want you to do. It'd be ridiculous if I have 50 subintervals for you to try to add this up. So we're going to try to do this using my sums of k's. Here's the given function, and again, I'm going to go, I need delta x as well as my x star. So delta x is defined as b minus a over n. I'll even have that definition on your cheat sheet. So it's going to be from 2, this is my b, this is my a, the interval from a to b, and then n is 50 subintervals. So the width of each rectangle is 1/25, or about 0.04 if you convert to decimal form. So the area, and let's see, who do we want to do? Left, right, oh, it says evaluate them all. Let's start with the left. So the area from the left would be the sum from k to be 1 to 50 of delta x times f of x star. Delta x times f of x star. I'll just write that out. We already know delta x is 0.04, and that's a constant, which can be popped out. So it's 0.04 times the sum from 1 to 50 of, go to the function and plug in my x star. Well, let's go find x star on the left. So x star on the left said a plus k minus 1 times delta x. I'll give you that formula. This case is easy because a was 0. That's nice because that term drops out. We'll just keep this k minus 1 times, we know delta x is 0.04. I'll distribute this and get 0.04k minus 0.04. So 0.04k minus 0.04. Now this is the part that sometimes students forget, but you're not done. You have to go to the function and evaluate the function at 0.04k minus 0.04, which means I'm going to take this guy and plug it into that x cubed plus 1 function. So I have 0.04 and times the sum from k to be 1 to 50 of 0.04k cubed plus 1, and let's see if we can type that in. A couple ways to get to the summation. You'll figure that out, but I like going alpha y equals, and if your calculator doesn't have this function, maybe you have an 83, you can't do this. There's an alternative method I'll show you in a moment. But if you have a TI-84, pretty simple. I'm going to go for x's instead of k's because it's easier to access my x than use my alpha keys. So I'm going to go from 1 to 50, which means I'm going to be adding up all 50 rectangles of this function, which we decided was 0.04 x cubed. I think I want to cube that whole thing. So let me go back and put in another set of parentheses here. And I can edit this by hitting second delete, which is an insert key. So another set of parentheses, cube it. This again, because if I don't add in here the innermost parentheses, then I start getting a funky large parentheses, and when that happens, I know I did something wrong. So again, I'm going to put this 0.04 x cubed in here. I know I was doing something wrong because I could see that I was cubing it out there, and I knew that that was wrong. So I went back and made sure I got that on the innermost parentheses, and I want that plus 1 as well. And don't forget, you have a times of 0.04 for the delta x. So I'm going to go back because I deleted this and restarted this over again. Let's see if I can get this. And a little bit tricky to type in, but I finally got it, 6.1616. Looking at this, it looks like I did the right. So I should have gone back. Shoot, I had 0.04, oh, the K, I forgot this guy right here. So this should have read, so this is for the right. The left should have said the delta x, the sum of K1 to 50 of 0.04k minus 0.04, that whole thing cubed plus 1, and then that one would give me, if I edit that, that should give me the 5.84. But again, another way to hit it is to go to, or to find that sum, is to go to your math key and then arrow up for the summation. If you like that a little bit better, that'll give that to you as well. So if you're doing that midpoint, you're going to end up with half of that 0.04, and that gives you the 0.02. And so here's the midpoint, which actually I think is pretty accurate. So if you have questions about how to type these in, by the way, there is a question like this on your test. So you need to know how to edit your calculators to find the sum. In fact, the question on the test actually asks you to demonstrate and write all this out. So it doesn't ask for the answer, it asks for you to show me what you're going to type into the calculator, and then it will ask for the answer. Remember, these are just approximations, so don't find the exact answer, find the approximation. This is a midpoint approximation. So you have to do it through this process. Good luck.